From this presentation, we will start analog electronics, and in the first lecture, we will complete semiconductor materials. They are the backbone of electronic devices and circuits. That's why it is very important to know what are the different semiconductor materials available to us and also their properties. So in this course, we will complete some topics like BJT, MOSFET, JFET. They are the field effect transistors and also the operational amplifiers. In short, we call operational amplifiers op-amp. So first we will complete the semiconductor materials before going to diode and BJTs. So let's start with it. The first topic is conductor. The term conductor is used for any material that will support a generous flow of charge when the voltage is applied across its terminals. We already know the flow of charge through a cross-sectional area in the given time is called as current. And we have to check for the amount of current flowing through the material, and depending upon this current we will categorize them in three categories. The first one is conductor, the second one is insulator, and the third one is semiconductor. So let's start with it. I have taken two examples for the conductor. The first one is the copper wire and the second one is the aluminum wire. You must have seen them in electrical equipments in your home. They are the most commonly used conductors. And if I cut this copper wire, I have a cross section that will look something like this. So we have a cross-sectional area A that is equal to pi r square, and the amount of current flowing through this cross-sectional area in the given time is very high. That is the definition for the conductor. The flow of charge is very high when the voltage is applied across its terminals. Whereas in case of insulator, we have the flow of current, or you can say the conductivity, is very low when the voltage is applied across its terminals. And the example that I have taken is mica and wood. This mica is very important in electrical industries. It is used for the thermal, and electrical insulation in electrical equipment. So it is very important. You must have seen it. And wood is definitely one of the insulator. So this is all for the insulator. The conductivity is really low, and you can say that the flow of charge is nearly equal to zero in this case. Let's move to the next thing, that is our semiconductor, and the most important thing that you must know in this course. So let's start with the semiconductor. What it is a material that has conductivity more than the insulators but less than the conductor. Very simple. That's why we call it semiconductor. So we can say that the flow of current in semiconductor is not as much as the conductor and not as low as the insulator. It is somewhere between the conductor and insulator, and because of this only we call it semiconductor. The two most important semiconductor material that you should know are silicon and germanium. Silicon is represented by Si and germanium is represented by Ge. They are very important and we will see their properties in a minute, but before that I will talk about the resistivity. In this we will see the resistivity for the conductor, insulator and semiconductor. Let's start with the resistivity first. What it is represented by rho, and it is the reciprocal for the conductivity. Sigma is the conductivity and rho is the resistivity. And in terms of resistance, we can write resistivity as rho equals to Ra by L, where A is the area of cross section and L is the length of the wire whose resistivity we are measuring. And it is the property of the material. This one is the property of material, and for every material it is fixed. And for unit, you can see we have the ohm, and we have a meter square for area, and in denominator we have meter for length. So the unit is ohm meter. Let's see the resistivity for the conductor. For conductor, it is 10 to the power minus 6 ohm centimeter. You can see the resistivity is very low, and it is obvious that if resistivity is high, the current is going to be low. because the material is offering more resistance, whereas if resistivity is low, the current is going to be more because the resistance offered by the material is really low. And for conductors, we know the flow of current is very high, that's why the resistivity is going to be low, and it is 10 to the power minus 6. And this 10 to the power minus 6 is specifically for the copper. This one is for the copper, and as I have told you, the resistivity is the property of the material, so it may vary material to material. For aluminium maybe it is different, so you have to write down in bracket that it is for copper. Let's talk about the insulator. For mica, it is 10 to the power 12 ohm centimeter, and you can see this is a huge amount of resistivity, 10 to the power 12. You can guess what amount of resistance this material is going to offer to the flow of charge. That's why we can say that the flow of charge is negligible for mica. Whereas if I talk about the resistivity of the silicon, it is 50 into 10 to the power 3 ohm centimeter, and for germanium it is 50 ohm centimeter. So you can clearly see that the resistivity for the semiconductor, let's say rho s is the resistivity of the semiconductor, is less than the resistivity of the insulator. So it is less than the resistivity of insulator, and it is greater than the resistivity of the conductor, rho c. So this is the relation that you must keep in your mind, and depending on this we have the flow of current through these materials. The flow of current will be reverse. If I say I is the flow of current for the semiconductor, then it is greater than the insulator and less than the conductor. So this is all for the resistivity. Now we will move to the next topic, that is the energy band diagram. I'm not going in much depth, I will just touch the surface of this energy band diagram. So let's see what is this energy band diagram. When the atom is isolated, let me draw the atom first. This is the nucleus having the neutrons and protons, and we have the orbits in which electrons are present, and we call these orbits as L, M, N, and so on. And this outermost orbit will have the valence electron because they will participate in the chemical reactions. This is a simple model for an isolated atom. Remember, this one is the isolated atom, but in general the atom is not isolated, it is present in the lattice. In case of silicon, you can see we have the lattice in which the atom is present, and it will form a particular structure that we will see in a minute, and thus the neighboring atom will have the influence on this atom, as well this atom will have some influence on the neighboring atoms. So what will be the change because of the neighboring atoms that we have to see? This outermost orbit will now split into the valence band and the conduction band. This one is the valence band, and this one is the conduction band. So we have a splitted outermost orbit, and the electron present in the conduction band will participate in the conduction. So if an electron is present in the valence band, we have to move this electron to the conduction band. And how we are going to do that? The only way to do that is to give this electron some energy, and the amount of energy that we have to give this electron must be equal to this gap. We call this energy band gap, or we call it as the forbidden band gap. We call this forbidden band gap because no electron is allowed to stay in this region. That's why it is forbidden. I will represent this gap by E naught, and in some books they will represent this gap by EG. So it doesn't matter, whatever representation you want to use you can. And in case of insulators, this is the energy band diagram for insulators, you can see it is very large, and hence the electron from the valence band will require more energy to go to the conduction band and participate in the conduction. That's why they are not good conductors, and they will not allow the flow of charge. And more precisely, E naught is nearly equal to 6 electron volt for the insulators, and you already know 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. So you have to give 6 times of this energy to make this electron appear in the conduction band. This is for the insulators. And if I talk about the semiconductors, definitely this band is going to be much narrower, and you can see here we have reduced forbidden band gap, and it is nearly equal to 1 electron volt in case of semiconductors. And if I talk about germanium, then it is 0.75 electron volt, and in case of silicon it is equal to 1.16 electron volt. Now you might be thinking, why in case of germanium we have 0.75 electron volt as the forbidden band gap, whereas in case of silicon it is 1.16. Germanium is having the lower energy band gap as compared to the silicon because of its atomic structure. If you see the atomic structure of germanium, you will find the number of orbits are more, and hence the force of attraction between the valence electron and the nucleus is smaller, whereas in case of silicon we have lesser number of orbits, and hence the force of attraction is more strong on the electrons. So you have to give more energy. You can feel it like electron is here and the nucleus is pulling this electron towards itself, and you have to give energy to make this electron appear in the conduction band. And depending upon the nucleus, if it is closer you have to give more energy, if it is far you have to give less energy. And in case of germanium, the force of attraction between the nucleus and the electron is smaller, whereas in case of silicon it is larger. That's why we have to give more energy in case of silicon as compared to the germanium. It is very simple thing. It is just pure chemistry that you have studied in your 9th standard. Now we can move to the last type of material that we have to see, and it is conductor. And you can see in case of conductors, the conduction band and the valence band is overlapping. There is no forbidden band gap, and thus the conductivity is very high because electron is free to go from valence band to conduction band, and it will participate in conduction without giving any extra energy to it. That's why the conductivity is very high. And this is all about the energy band diagram, and you have one more definition to write in your exam. If someone asks you what do you mean by the semiconductor, you can easily say that it is the material in which the forbidden band gap is nearly equal to 1 electron volt. Whereas in case of insulators it is nearly equal to 6 electron volt or more than it, and in case of conductors they overlap each other. So this is also a point that you have to write in your exam. Now we will see the periodic table so that we have a better idea for the position of the germanium and silicon, and we can predict some of the properties from this periodic table. So let's move to it. This is the periodic table, and I hope you know how to use a periodic table and in what manner the elements are distributed to the different groups. Actually, they are distributed depending upon the number of electrons in their outermost orbit. And in case of silicon and germanium, that you can see here, this is silicon and this one is germanium, they belong to group 4. And why they are in group 4? Because they have 4 electrons in the outermost orbit. You can see in case of silicon the total number of electron or the atomic number is 14, and you can have the electron in the first orbit, the maximum number of electron in the first orbit equals to 2. So we have 2 electrons in the first orbit. Then we have 8 electrons, so 2 plus 8 is 10, and finally we have 4 electrons. So you can see 4 electrons are there in the outermost orbit, whereas in case of germanium we have 32 electrons. Let's have 2 electrons in the first orbit, then 8, then 18, and then 4. So germanium is also having 4 electrons in its outermost orbit. Now there is one very important thing that you should keep in your mind, that every element will want to have a stable state, and for that they must have the noble gas configuration. This is the group for the noble gas. We have helium, neon, argon, krypton, xenon, radon, and the silicon will try to have the configuration for argon, that is the 18 electrons, and germanium will also try to have the configuration for the krypton, that is 36 electron. So they need 4 more electrons to have the noble gas configuration, and we will find a way so that they will have 4 more electrons. The unique qualities of germanium and silicon are due to their atomic structure. The atoms of germanium and silicon forms a definite pattern that continuously repeats itself. One complete pattern is called crystal, and the periodic arrangement is called the lattice. In this presentation, when I make the atomic structure for silicon, I will explain you what is this pattern and how we can have this pattern by the covalent bond. Okay, I will make the atomic structure for silicon quickly. This one is the nucleus. Then we have our first orbit, and in this first orbit we have 2 electrons, as I have already told you. Then we will have our second orbit, and this second orbit will have 8 electrons. Let's make this 8 electrons quickly. It's like we are doing the problem of 9th standard, but these things are really important in analog electronics. So we have 2 electrons and then 8 electrons. In total we have 10. We need 4 more electrons to make 14 electrons. This is circular. I'm not making it circular. So let's add 4 more electrons. Okay, so this is the atomic structure for silicon, and we want to have 4 more electrons in this silicon so that it attains the noble gas configuration. To do that, we will make a covalent bond. We have 3 types of bonds. The first one is the ionic bond or electrovalent bond, in which the donation of the electron is done. You will donate the electron to some other entity completely, whereas in case of covalent bond we just share the electron. So we are going to see how by the covalent bond we can have the 8 electrons in the outermost orbit. I will copy it down and then I will paste it. Okay, I will copy and paste again. Now you can see we can have the covalent bond between these 2 electrons and these 2 electrons, and we have to focus to this particular atom. We don't have to see for these 2 atoms. We will see for this atom. We will try to have 8 electrons in the outermost orbit of this atom only for now. And you can see we have 1, 2, 3. This electron is shared. 4, 5, 6. Okay, so we have 6 electrons. We need 2 more. So I'm going to paste 1 more silicon atom, and finally the last one here, and I will make 2 more covalent bonds, taking these 2 electrons and these 2 electrons. So we have 7 and 8. So we have 8 electrons for this silicon atom, and this is the pattern that I was talking about, and this is one complete pattern, and more patterns like this will make our lattice, and that lattice is used in the diode, BJTs and other electronic devices. So we are moving to the important topics real quick. You have to keep this configuration in your mind. It will help you to understand intrinsic and extrinsic semiconductors. So this is all. We are already pushing our time. In the next presentation we will study about the intrinsic and extrinsic semiconductor as well as the electron and hole concept.